So hello everyone, this is lecture 12 for the atomic physics. In the last lecture we have completed the fine structure. In that we have stated that how the relativistic effect due to the spin orbit coupling and that there is this deviation or the shift in the energy levels due to the relativistic effect and spin orbit coupling and both combined is called the fine structure. So that's how we get these structures. That first it was Bohr, then it was this Dirac equation, and we get these that for same J and N we will get the same level. There will be degeneracy here. So and we get these 5 lines, but in the experimental values we know that in the experimental values we get 7 components in the H alpha line, that is 3 to 2 transition, but here we are getting only 5 components according to the Dirac equation. So what is the factor remaining? So it was given by the Lamb, means Lamb introduced a Lamb shift, and that is how we explained the 7 lines. So what is Lamb shift? The interaction between the vacuum energy fluctuation and the hydrogen electron. So we don't need to understand this what is vacuum energy fluctuation. It is there, you will study in the higher studies, meaning the PhD or all, if you go to the higher energy physics. But here just remember that there is this vacuum energy fluctuation and the hydrogen electron. So there is an interaction between them that will create some potential energy, and that is again gonna disturb this degeneracy, means this degeneracy will collapse, and there will be, means here you are having the same level, but now this level is also split into two, and that's how this degeneracy will be broken due to the interaction between the vacuum energy fluctuation and the hydrogen electron. In these different orbits break the degeneracy observed in the same energy levels by shifting one of the levels in the upward direction, for example. Means that's how the level will shift. Means this you have here this 2s half and the 2p half. So this 2s half will be shifted upward, so here you will get one another level. Just like here you have this first these both were in the same level, but now degeneracy will broke and this 2s half you will get here. And this energy gap is 10% of the complete energy gap between 2p3/2 and 2p1/2. That's why it is visible here in the, and that's why we will get different lines because of this. So this will be your degeneracy broken now, and that this is called the Lamb shift actually. Okay, so similarly you can see here also, means in the 3p half and 3s half, here this 3p half and 3s half, this 3s half will shift to the upward, and you will again get the Lamb shift, and there will be this degeneracy broken again here, and this difference is again is 10% of this complete difference. And if you see here also in this 3p 3/2 and 3d 3/2, then again this p will shift upward, but this difference will be very small as compared to, I mean, this is 2% of the energy gap between 3d 5/2 and 3d 3/2. This is negligible. That's why we consider this one as a single line, but there is also some shift there, but we just consider it as single line because that much resolved spectrometer we don't have that can split these two also. Okay, so this shift is the energy level is called the Lamb shift. Due to this shift, degeneracy predicted by the Dirac is removed. Now degeneracy is removed, so we will just see these were the Bohr lines, and now energy levels. Now in the Dirac equation we get these, means this is the shift, and this is the two, means these lines you get after the Dirac equation. But now when the Lamb shift is introduced, so this is shifted little bit upward, and these two will distribute into a 2, and this will remain here it is. Now again this 3s by 1 upon 2 and 3p 1 upon 2 will be splitted, so 3s by 2 will go upward, 3p by 1 upon 2 will go downward, and it will, as I told you, this difference is very small between these two lines, so we'll just consider it as 1, and this 3d 5/2. So now you will check that according to this rule, delta L must be plus minus 1, delta J must be 0 plus minus 1. So you will get these 7 lines, you can just check them and you will get that all these lines satisfy these rules. This is the electron dipole transition, so they follow these, and that's how you explain the 7 lines. So that's how Lamb shift we gave us the correct structure. You must remember this, it can be asked in the interview. Now there is a question based on this. The electron of a free hydrogen atom initially in a state within quantum number n equal to 3 and L equal to 2, it then makes the electron dipole transition to a lower energy state. Which one state could it be after transition? So initially it is n equal to 0 and L equal to 2. So at n equal to 3 you will have value of L as 3. 3 L values will be there, 0, 1 and 2. And now there can be transition, means only 2 and 2 is given here. So for n equal to 2 there will be L equal to 0 and 1. Now see, for this rule to follow, means delta L must be plus minus 1, so it can't go to 0, and it is already here, so it can go only up to the L equal to 1. So that's why the transition will be, final transition will be n equal to 2 and L equal to 1. So this will be a correct option. So you must remember these rules, very important rules are these. Means question is framed according to these rules a lot of times. Now there is this last topic for today, that is intensity ratio for doublets. So they can ask you that this intensity ratio means if you have this 3p to 3s transition, then you will have 3p 3 by 2 and 3p 1 upon 2 to the 3s 1 upon 2. This is single level. Now there will be two lines because of this, and both these lines have different intensity. So if you need to find the intensity ratio for these, so IB will be equal to proportional to the J value. So always remember this of this level. So it will be IB by IA equal to 3J for this plus 1, and for A it will be J is half, so 2 half plus 1. This will be your intensity ratio for IB to IA. But see, there is a little bit complex example also like this. Means you have two levels for P and two levels for D. D to P transition is there. So now there is three lines are possible according to the electron dipole transition rules. So now how you can find the intensity? See, here only one final level was there, that's why you will get single equation. But now there is two and there is two, so we will get two equations. So first for this, so it will be IB, means initially only it is IB, divided by, now transition from this is because of these two, means intensity because of these A and C transition. So that's why intensity here will be proportional to A and C, sum of A and C. This will be IB divided by IA plus IC equal to, IB is proportional to 5 by 2, so 2 5 by 2 plus 1. And for this it will be for A and C it is proportional to 3 by 2, so 2 3 by 2 plus 1. Now this is one equation. For second equation we will take these two lines. So for this first one it is proportional to sum of A and B, and for this it is proportional to C. So for C it will be IC divided by IA plus IB, and IC will be proportional to the this J, that is half, and for this IA plus IB it will be 3 by 2, so 2 3 by 2 plus 1. So you will get two equations from here, and now you just can easily find the ratio, and you will get the ratio as 1:9:5. So they can ask you a question based on this intensity ratio for doublets. So you must remember these all things as I told you. And in the next lecture we will start the LS and JJ coupling. So that will be, means now up till here we just discussed the one electron system, or the atoms, means hydrogen like atoms we have discussed. But from the next we will study about the atoms which have more than one valence electrons, that how can we just make the ground state for them, and how the energy levels will be there for them. So that is all we will discuss in the LS and JJ coupling, and we will move forward. So that's all for today. Thank you everyone.